This is a reassessment of the standard rotational dynamics, and this is problem number 53 of chapter 5, page 188. In a beam's ultracentrifuge, the rotor is suspended magnetically in a vacuum. Since there is no mechanical connection to the rotor, the only friction is the air resistance due to the few air molecules in the vacuum. If the rotor is spinning with an angular speed of 5.0 times 10 to the 5th radians per second, and the driving force is turned off, its spinning slows down at an angular rate of 0.40 radians per second squared. Part A, how long does the rotor spin before coming to rest? And Part B, during the time, through how many revolutions does the rotor spin? So first we list our knowns, or what is given in the problem. And we have the initial angular speed is 5 times 10 to the 5th radians per second. We know our final angular speed is 0 radians per second, and our acceleration is negative 0.4 radians per second squared. So we can use the kinematics equation. The final angular speed minus the initial angular speed is equal to the acceleration times the change in time. So we plug in our final speed, which was 0 radians per second, minus our initial speed, which was 5 times 10 to the 5th radians per second, is equal to the acceleration, which is negative 0.4 radians per second squared, times delta t. Then we want to find delta t, so we divide each side by negative 0.4, and we get a delta t of 1.25 times 10 to the 6th seconds. So once we have this time, you can take that, you can plug it into another kinematic equation to find part B. And part B is how many revolutions. We're trying to find the revolution, so we need to find radians per second. So the change in radians per second. And so we have our initial angular speed, which is 5 times 10 to the 5th radians per second, times our delta t, which is 1.25 times 10 to the 6th seconds, plus 1/2 acceleration, our negative 0.4 radians per second squared, times delta t squared, which is 1.25 times 10 to the 6th seconds squared. So you solve this part and you get 6.25 times 10 to the 11th. You solve this part and you get minus 3.125 times 10 to the 11th. The change in the change in radians comes out to be 3.125 times 10 to the 11th radians, and then to get that into revolutions, you multiply that by 1 revolution over 2 pi radians, so that way the radians cancel and you're just left with revolutions, which is equal to 0.497 times 10 to the 11th revolutions, or 5 times 10 to the 10th revolutions.